Welcome back, guys. Now we have another problem in boiling, which is also associated with radiation. So now we have a heating element here, which is 8 mm in diameter, and the emissivity is 0.92. It is submerged in a water bath horizontally. So the surface temperature of the metal is 260 degrees Celsius under steady state boiling conditions. So you have been asked to calculate the power dissipation per unit length of the heater. So please assume that the water is exposed to the atmospheric pressure and it's steadily heated. So now let's start writing the given data. So the first data you see is that the diameter of the heating element, which is 8 mm in SI units, it's 8 into 10 power minus 3 meters. The emissivity epsilon is 0.92 and the wall temperature is 260 degrees Celsius. So you have been asked to find out the power dissipation P or Q. So now you see here the saturation temperature of water is 100 degree Celsius, and you see the delta T temperature here is TW minus Tsat, which is 260 minus 100. The previous problem was about nucleate pool boiling, and now this is film pool boiling, in which you will be calculating the film temperature, which is TW plus Tsat divided by 2. So this is going to be by 2, and the film temperature is 180 degrees Celsius. It is at this temperature you are going to find the properties. So this is going to be a vapor. Remember, at 180 degrees Celsius there is no point in finding out the properties of water. You know that water doesn't exist at gaseous state at 180 degrees Celsius. It's going to be a water vapor. So at 180 degrees Celsius, so you have to go to the HMT data book, page number 39. You have to find out rho V, which is the density 5.16 kg per meter cube. kg per meter cube, and Kv, which is the thermal conductivity of the vapor, watt per meter Kelvin, and then the specific heat capacity of the vapor 2709 joule per kg Kelvin, and the dynamic viscosity of the vapor. You also look at the properties of water at 100 degrees Celsius. So we need some values to be substituted into the relation. For example, this density, it is going to be 961 kg per meter cube. So these values could be obtained from steam tables, page number 4, like we did in the previous problem. So, and also the HFG value, which is 2256.9 into 10 power 3 joule per kg. So these are the two values you should be noting down from the steam tables. And now for film boiling conditions, so heat is transferred by both convection as well as radiation. So the net heat transfer coefficient is heat transfer coefficient due to convection plus 3/4 of the heat transfer coefficient by radiation. So this, you know, this value of H, equation of H convection, you can get it from the plus 0.4 CPV delta T divided by mu V d delta T whole power 0.25. So this is going to be your equation. This is available in page number 142 of your data book. Alright, so now let's start substituting. So kV is the thermal conductivity, which we have already noted down. So whole cube into 5.16 into 961 minus 5.16 into 9.81. So into HFG is 2256.9 into 10 power 3 plus 0.4 into 2709 into 160, which is this delta T, and divided by mu is the dynamic viscosity, 15.10 into 10 power minus 6 into diameter is 8 into 10 power minus 3 meters, and this delta T is 160 again. See, so now you have to solve this by using calculator very carefully. So do it term by term instead of doing it as a whole again. So you will arrive finally at power 6 divided by 1.93 into 10 power minus 5 whole power 0.25. So now we have H convection value as 421.02 watt per meter square Kelvin. So this will be your heat transfer coefficient due to convection. Now this heat transfer coefficient due to radiation will be sigma epsilon TW power 4 minus T sat power 4 divided by TW minus T sat. So this equation is once again available from HMT data book, page number 142. So sigma is nothing but the Stephen-Boltzmann constant. So remember, this is not surface tension like we did in the previous problem. So this is Stephen-Boltzmann constant. Emissivity is 0.92, which is given in the problem. And now TW is, see, one point here I would like to emphasize is that you have to substitute all the temperatures in Kelvin here, not in Celsius. So 260 plus 273 whole power 4 minus saturation temperature is 100 degrees Celsius, which is you have to add Kelvin. You have to substitute these two values, H radiation and H convection, in this equation. Now H, the overall heat transfer coefficient, will become H convection plus 0.75 of H radiation. So this will be 421.02 plus 0.75 into 20. So the overall heat transfer coefficient will be 436.02 watt per meter square Kelvin. So then you should also find out the heat transfer, which is the power dissipated HA delta T, which is nothing but H into pi dl. Since this is a rod, the surface area of the rod is pi into d into L, TW minus T sat. So H will be 436.02 into pi into d. The diameter of the element is 8 into 10 power minus 3. So it's per unit length. So substitute 1, and then the difference between the temperature is 160. So finally the power dissipated is going to be 1753.34 watt per meter. So this is the power dissipated.